Okay. Today, I will share with you my experience migrating over 300 ingestion processes from a traditional ETL approach to a complete new serverless architecture on AWS. The challenge and lessons learned through the process, such as the new platform, allow us to increase the efficiency and improve the performance of processes and the costs associated with the cloud. I hope you find it interesting. Who I am? I am a telecommunication engineer. I study at University of Seville. Since 24, I have been working as a center where I have participated in different national and international development and maintenance projects. I started doing billing projects for telecommunication companies, and later I moved to business intelligence projects for different industries, where I have developed most of my experience. I have worked on the entire life cycle of the data, from ingestion, transformation, analyze, working with different technology. I have been a speaker in a master class about big data. And additionally, I have been a lecturer at the university, participating in employment forums to get the world of data closer to the student. The agenda that we will follow is, first of all, I will give you a context of the project. Secondly, we will review the initial architecture. Then we will move on to the proposal and the solution developed. And finally, we will analyze results of the project. Let's start. Once upon a time, there was a supply distribution company with more than 21 consumer and energy marketlets in more than 5 countries. The company had information in a big data environment for the application of machine learning models that allow it to operate in the energy market. More than 250 different file types were loaded in near real time from different sources using an ETL tool. Due to the cost of the licensing, they request to us to re-engineer all the flow using big data technology. The goal was to achieve the complete dismissal of the ETL tool in less than 5.5 months. Before getting into the new architecture, let's review what the initial situation was. The following diagram shows the original architecture. Files were deposited in a folder in S3. There was a daemon scheduled in Cloudera H node, which was in charge of checking if there was any new file pending to be uploaded or to be reprocessed every 90 seconds. If there was any file, it creates an auxiliary table with the list of tables pending to be loaded. A child process was launched for each type of file, pending to be loaded if it was not running previously. Each file was downloaded to the H node, copied to a backup folder, and removed from the input folder. The ETL was responsible for flattening the data and put it into AWS in the ingestion layer. Later, the ETL transformed the file adapting to the format of the consolidation table and loading into an auxiliary table. An Impala shell process was launched then, which was in charge of updating the partition of the entity consolidation table based on the information in the receipt file. Finally, audit records were stored in the relational database to identify how the process had ended, if there was an error, where the error had occurred, and the start and end data time. Have you detected any weak point in this architecture? Yes, it is not an event-oriented architecture. It was based on periodic check on the input folder. Certain file may not be processed for up to 90 seconds if they arrive just after the daemon has checked if there is a new file. Once we have clear idea about the initial architecture, let's move on to the proposal. As we have mentioned it before, the goal is the decommissioning of the ETL tool in less than 5.5 months. The requirement that we had to meet with the new architecture were all files must be loaded in less than a minute. Additionally, only files with the same type could be in queue. It means that file of a certain type could not affect the loading of another type. Consolidated data must be available through Cloudera using Impala. Files are received in the S3 buckets, as in the initial architecture. And there are more than 250 files of different types with different formats, some of them quite large. The first point is to ensure that the proposed architecture is able to support the previous requirement. And for that, we had some aspects that we had to review. It was necessary to ensure that the current sources are loaded correctly in the new architecture. Additionally, test that unless one file for each format was ingested successfully. Validate that the biggest file could be processed. If there is a problem, find out an alternative solution. Carry out a stress test to identify possible bottlenecks in the new architecture. And finally, to evaluate the duration of the process between the new architecture and the old one, obtaining better time. As a result of the proof of concept we obtained, the result of the test carried out confirmed that the new architecture supported the existing requirement. A fair approximation of the cost reduction that it will provide, and we obtained the necessary data to be able to estimate the team we need to carry out the project in the requirement time. After the architecture was confirmed, our proposal was based on a process of continuous values increase, which can offer tangible solutions and real products in a limited period of time. Agile allows all of the people involved to interact on technological process and tool, maintaining an environment of motivation and constant collaborative work. We defined 6 sprints of 4 hours each one, where we will develop processes from less to more complex. The sprint 1 with very simple flat file. Sprint 2, simple flat file. Sprint 6, flat file of medium complexity. Sprint 4, complex flat file. Excel of medium complexity and web service. Sprint 6, complex Excel, JSON file, and XML of medium complexity. At the end, Sprint 6 with complex XMLs. At the end of each sprint, loading processes developed were stopped in the ETL tool and activated in the new architecture. This allows us to identify possible issues in advance and fix it. Additionally, once the first sprint was finished, and with the new process running in the new architecture, they were no longer developed in the ETL tool. The new ingestion process that the client was requesting were developed directly in the new architecture. The next step was to ramp up the team that will develop the project. 3 necessary profiles were identified. The first one, people who have experience in the system architecture. These resources will allow us to generate the design of the different transformations that were performed for each type in the ETL tool. They will give support to the dev of the team that developed the project, and it will also help us in the preparation and validation of the tests necessary to ensure the correct result of the new architecture. It will provide a sample file and the result of loading them using the ETL tool. A second profile with experience in the new architecture to design the process following the best practice in this technology, ensure the quality of the deliverables, and training and supporting the new joiner. And finally, new joiner with training in the new architecture to design that will be in charge of developing the process and testing them with the help of the most experienced team members. We have a team, we have a methodology, and a plan. Now, I would like to look at the new architecture. You can see the diagram of the new architecture, where we have different layers. The buckets, the enterprise service bus, queue, transformation, ingestion, consolidation. The technologies used are the enterprise service bus, which is responsible for collecting the file from the source system and sending a message to a SQS queue. The bucket, AWS S3, as in the initial architecture. AWS SQS that receives the message and triggers the process to load the file. AWS lambda for file processing. HTTPS to upload the information to the Calero cluster. Impala for launching Consolidation Query. Let's dive into the different technology. Amazon Simple Storage Service is a service for object store. In the project, a further structure was created to support file management. The different processes that interact with them access and move the file between this folder. There is an input folder where the enterprise service bus deposits file for ingestion. If a file fails for some reason, when it's processed, the file is moved to an error folder. Files are tried to be processed 3 times automatically. Files that have failed more than 3 times are moved to a folder in which they are analyzed. And after detecting an error is done, it is claiming to the source system. The Impala query are stored in another folder from which they could be retrieved for Lambda to consolidate the information in the Calero cluster. The XSD file for the validation of the received XML files are also found in S3. If for each currently processed file, a copy is stored in a backup folder. If an error is found out in the future processing it, it can be retrieved from the bucket. HQS Amazon Simple Queue Service is a fully managed message queuing service that allows us to decouple and scale microservices, distributed system, and serverless application. If you remember, one of our requirements was that only file of the same type could be in queue. For this reason, a queue is created for each type of file. When the file is deposited in the X3 input folder, a message is sent to the queue associated with that type of file. The queue is FIFO. In this way, we ensure that the files are processed in the same order that they are generated. To ensure, someone may ask, what happens when file is reprocessed? To ensure that the information is always processed in order, the file name has the generation date and time. This allows us to identify the most recent information in the consolidation process. Receive message has 3 attributes. The file name that allows us to know the field that we have to retrieve from S3. File type, to get from the RDS database the information necessary for its treatment. The type of flow. In this project, there are 2 different flows according to the requirement of the user. Finally, the SQSQ triggers the lambda associated with the file type of the queue. AWS Lambda is a serverless event-driven compute service. Lambda is the function that performs the necessary transformation for each type of file to get the format required in the Cloudera consolidation. All developed Lambda has a common structure. After receiving the event, it retrieves the values associated with it, read environment variable and parameters from the RDS. It checks that the file received within the message exists in S3 and loaded into a data frame. The file is flattened and stored in the staging area in Cloudera. For this, HTTPFS technology is used. It performs the necessary transformation on the input data frame to build a file according to the format of the consolidation table and load it in a Cloudera auxiliary table. Once the file is in the auxiliary table, the consolidation query is launched using Impala, auditing the partition affected by the received file. The evolution of the process is recorded in an audit table in the RDS database. And if an exception is raised, it is caught and handled. The file is moved to an error folder for further processing or review. Finally, if it is necessary, Lambda function can invoke a REST API that can trigger machine learning model or some notification process to the user. The developed Lambda are supported by common libraries included within the layer. A layer is a zip file, a sheet that can contain additional code or other content. A layer can contain library and allow to reduce deployment, package size, and to promote code sharing. As a result of the proof of concept, different methods were identified that could be reused by the different lambdas. Obtain Calero ticket, get common parameter, function to interact with RDS, method to launch in query, change date format, update audit table, check if the file exists in S3, send a message to a queue, invoke REST API. They are examples of reusable methods. In some cases, it is necessary for our process to send a message to a certain queue. An example of this case, it is when a compressed file is received that contains files of different file types inside, or when it is necessary to reprocess a file that previously ended up in error. In this case, steps that are followed by the lambda are: first, it decompresses the file or retrieves the file pending processing from the error folder. For each file, the file type is determined using the mask associated with this file name. This is a value that is stored in the RDS. Once the type has been identified, the queue is also retrieved from the RDS. We already have all necessary information. The file is moved to the input folder, and the message is generated and sent to the obtained queue. AWS Lambda established a series of quotas that we need to consider. In particular, in our project, the most significant are function timeout. The maximum duration of a lambda cannot exceed 15 minutes. Function memory allocation. The maximum memory that the lambda can use is 10 gigabytes. In our particular case, due to client restrictions, it is 3 gigabytes. Some files have a high size and require resources that greater than the quota. To solve this issue, two possible options were identified. The first one is to split the processing of the file within the lambda into smaller blocks. This allows to reduce the memory consumption. In case in which the first ones were not enough, a REST API can be invoked in the Cloudera edge node to process the file by using a semaphore to prevent Lambda from starting to process a new file before the previous one has finished. This is a system that was already implemented in the ETL tool to avoid concurrency issues. AWS CloudFormation. Let your model provision and manage AWS and third-party resources by treating infrastructure as code. This slide shows the code for defining a SQS queue, a layer, and a lambda, as well as the event that the queue generates and the invoke permission needed by the SQS queue to invoke the lambda. If we look at the picture, we can see that the SQS queue is defined as type FIFO, as previously mentioned, to ensure that the messages are processed in the same order that is were received. If we look at the lambda, you can see a reference to the layer to be able to use its library. Finally, we observe that both the lambda invocation permission and the event source mapping, we can identify how the SQS queue is related to the lambda. GitHub. How do we implement GitHub? The following tools were used. Bitbucket as a Git code manager. It allows version control to tracking and managing changes to software code. Bitbucket allows us to use branches and merge the code developed by team members. Additionally, it provides us a history of the change that the code has suffered. Bamboo as continuous delivery pipeline. With the commit on the master branch, a plan is triggered in Bamboo that deploys the infrastructure and code to the AWS development environment. It also allows us to select the version of the code and infrastructure to deploy in each environment. And at last, AWS CloudFormation, infrastructure as code, deploying infrastructure template and managing the different dependencies between the components, rolling back if it is necessary. As a result of this project, a total of 323 ETL processes were migrated. To give you an idea of the load that the architecture is able to process, approximately 8,000 files are unloaded daily to the Cloudera cluster, and the average time of this ingestion is 45 seconds. The new architecture has reduced the load time on average by 65% compared to the previous one. And if ingestion processes are stopped, for example, before an action in the cluster, the time to reproduce all the accumulated file during downtime has been reduced about 40%. Finally, taking into account the cost of the ETL tool licenses and the cost of the new architecture in AWS, the annual cost reduction is about 52%. In conclusion, then, it is clear that the new platform allows us to increase efficiency and improve the performance of processes and the cost. Thank you for your attention. I'd be glad to answer any question you may have.
All right. So we've got 3 questions here. Okay, cool. And then somebody, Anonymous Goose, is writing a question. So thank you so much, Juan J. One of the questions that we have here is regarding the project, like what was one of the most difficult times of the project that you were discussing?
In the last sprint, we had to develop a XML file. It takes so much time loading into data frame. When I talk about a long time, we are talking about 45 minutes or an hour and a half. We are using Python library. We try with different technology to flatten in the file in order to make easy the load into the data frame. At the end, we start with AWK, and the result was wonderful. Can someone estimate how long take AWK to flatten the file? From 45 minutes.
Any takers? Can anyone guess how long it took? No?
Seconds. So it's important to know different technology, to know which is the best technology to use for each case.
So I have another question here, and it says, I'm trying to figure out if this is a continuation of the last question. So it says, what are average file sizes, total amount, and gigabytes? But I'm not sure if it's related to the third question here that somebody included.
How is the right?
I think this is a completely separate question. It's just indented.
The average file size, I don't know. I'm not sure. but we have file from kilobytes, and other greater than we have already loaded file from 3 gigabytes, a very big file. For this case, we use a REST API in the edge node because this type of file need a lot of memory, resources greater than the quota. So we have implemented for some time that have a high size, a threshold. If the size of the file is greater than this threshold, we invoke a REST API and it is processed in the edge node in Cloudera. With the decommissioning of the ETL tool, the Cloudera edge node has more resources. So we load using the Cloudera edge node. And we use a semaphore method to avoid that the lambda begin to work with another file until the before has ended.
Okay. And then there's a question here. I think someone's asking you to clarify. It was done in 5.5 months?
Yeah.
Okay. And then another question here I have is, was there any type of file that required special treatment?
Yes. There are some files with small size. A high number of them are received in a zip folder. In that case, we process all the files sequentially in the same lambda without launching the consolidation. And we have a time, and we are processing the all file until before sharing a specific time, to not reach the limit of the AWS duration. When this limit is reached, we launch the consolidation query for all the files. This allows us to reduce the number of Cloudera queries that we launch and improve the performance of the process of the file type. One important thing in this architecture is the consolidation query. Because we have to identify the partition associated to the criteria of consolidation and to the way the user is going to access the data. When the file is loaded in the auxiliary table, the query, the first thing that it does is to obtain the distinct value of the column that define the partition, and then collect from the consolidation table only the partition associated to this value. This allows us to reduce the volume of data collected by the query and improve the performance.
Okay.
Some tables are very big, and limit the volume of data that we process is very important to obtain that the files are loaded in less than 1 minute.
Did you say less than 1 minute?
Yeah.
Okay. Wow.
Yeah, maybe 45 seconds.
Sorry?
45 seconds.
Okay.
We ingest the file.
All right. Well, I think that we have to close out for now, but will you be around a little bit later in case other people in the audience have questions?
Yes, of course.
They can find you in the halls.
Oh, yes,
Yeah?
of course.
Okay. Well, let's all please give Juan J. Calero a very big round of applause. Thank you so much.